Okay, this is hopefully the start of this. Hi, I'm Glenn Dane. I'm here to tell you a little bit about metamorphic manufacturing. I'll start with what the word means. We've had two waves of digital manufacturing. We've had CNC cutting, we've had additive manufacturing, which is cut, add, and the next obvious one is to do things by reshaping. And metamorphic means we're changing the shape and the properties of metals as we process them, and that is a new digital manufacturing technology, we believe. And that's what we want to promote. This is work that comes out of the Light Metals Manufacturing USA Institute lift out of Detroit, and it's based on a study done by TMS. And there are collaborators with LIFT and Ohio State indicated here, and I'll say a little bit more about them as we go through. And let's see if this slide change works. It seems to be. And the point is, this is a new way of making things. Metamorphic manufacturing is that, by making things by digital reshaping. Right now, this isn't easy to do, but we believe that all the basic technologies are there, and this can give us a high quality, agile, and low energy way of making things. Basically, what this is robotic blacksmithing, basically taking the things a blacksmith would do, where he can basically see with his eyes, make decisions, and then bang on things to make shapes. And we can make very incredible things with that. But the problem is, old school blacksmiths, you don't want to trust those with your lives. You don't want to put parts made by a blacksmith on an airplane because you don't know if you might have had too much mead the night before, something like that. So you want something where you have control, where you can actually record everything that's happened, and that's what you can get if you have computers in control. So first of all, let me say, what is forging? This is an example of closed die forgings on this slide, where you basically make dies that have a shape into them, squeeze material into shape. This gives you things with awesome properties. It can be expensive, and it can be a long time to the first part because you first got to make tools. You can also do things with open die forging, where you don't have the shape in it. You can take small bites. This is used regularly also, usually for big things is common. But you usually don't make it to make complicated shapes when you've got open die forging. That's what this is really about. It's using computers and open die forging to make complicated parts. We'll see what that is as we go. The other place this fits is this is a form of digital manufacturing, where the part description is stored on the computer. We make the part without fixed dies, without fixed molds. That allows us to do things that are flexible. We can do rapid product changes, have short lots. We can do things that are sustainable, and we can manufacture where things are needed. That reduces shipping and overproduction, which are actually both significant causes of carbon footprint. We can reduce it by using this technology, we believe. So we position metamorphic manufacturing as the third wave of digital manufacturing. The first wave started in 1949, where we started using computers to move cutters around, a little bit like an Etch-a-Sketch, to make shapes. This is something that's been evolving ever since it started at MIT back in the 1940s. Basically, in the 1980s, some people had the idea, well, why can't we make things by adding things, but make things by adding material to develop a part? That was developed in several locations. MakerBot came around the 2000s and made this very widely known. Lots of techniques were used, and we've even made things like full auto bodies at the auto show, and this was done by Oak Ridge National Lab, and President Obama sat in the car and all. It's a great demonstration. But again, these techniques have some limitations, and we think if we do things by reshaping digitally, we can get by some of those limitations. So again, here's what metamorphic manufacturing is. We're going to use digital reshaping to change shape and change properties. And the basic things you need with that are sensors, thermal part, back in the day it was dragons, an actuator, which can bang on things, robots that can move things around, that's this arm, and then you need computation that brings it all together. And today there are ways we can do this far better than a blacksmith ever could. We can replace the dragon with lasers, with induction heat, all kinds of things. We can replace sensors with things that can give you dimensions very precisely and temperatures. We can do computation that is very precise in recording. And the actuator systems can be far greater than the 1 horsepower or so that a blacksmith could do. You can do things with big machines that can really crunch material together. So to move this forward, ONR funded a study that TMS did. We brought together a great group of people. You can find the report in its entirety in open source down here at tms.org/metamorphic manufacturing. And the goal of this was, how do we take these moving forward technologies, turn that into a commercial activity in the next 3 years or so. Brought together some of the best possible people we could find. I'll let you read about their credentials here. Suffice to say, all are deeply knowledgeable people that come from academia, industry, and government, and can help us drive things forward. The ideas upon which this is based is we take open die forging, where we can make really big things, and this is common already. We do robotic blacksmithing. This is an example from David Bourne, one of the people on our committee, who made robotic bending systems, where you basically use press brakes that would basically reposition the bend elements, reposition the part, and you can make all kinds of parts with that. So these are some of the foundational ideas that already exist, or already commercial. To consider what's next, Lyft put out a prize where they said, we'll give $25,000 to a team that can make 2 out of 3 components, and these are 2 of 3 components that were chosen. The other one was a goblet. And if you can make one system that can, just by changing the software, make 2 of these, you can win, and the best team wins. The best team happened to come from Ohio State, this group down here, known as Team Honey Badger. They've got a website with more detail. But you can see what they're basically doing. They're taking plasticine. Plasticine was chosen because it behaves like metal at high temperature. It basically conserves shape, or conserves volume, but you can reshape it. They developed a reshaping system that was basically an add-on to a CNC milling machine, and let that go to basically reshape the plasticine in a computer-controlled, agile way, and made these parts, got very close to them, and you can see the elements. You've got squeezing, you've got tool changes going on, and just by changing the software, you can make a wide range of parts out of plasticine. There's far more detail. It's in a report that's on that site that I've mentioned. And here are examples. This is the target geometry. This is what was actually made. You see they're pretty darn close. And this is detail of how the system was built. On the top right, we see a CNC milling system that has this squeezing arm that's on it that can be repositioned and changed in angle. And the movable bed changes it in position. We've got changeable tools. There's a control system that works with this, and software. And a lot of cleverness went into this by the system. A lot of cleverness went in by the students who brought this together. Basic ideas are relatively simple. Basically, if you're a technical person, you know that if you're doing plastic deformation, volume is conserved, but you can change shape. And if you want to do something like change a sphere into a cube, if you do just enough squeezing and turning, you get very close to a cube after a while, after the deformation happens. We can do this with plasticine, or we can scale up and use something like a 20-ton C-clamp. You can put a little actuator in that and take small bites, and you can get plastic deformation. If you can take a 20-ton clamp and put a little 1-inch square actuator on it, you can take small bites, and again, much like you saw in the last thing, make anything you like out of metal, be it hot or cold. So again, these are the foundational elements turned into a mission badge by the TMS group. We have sensors, thermal control, actuators, robotic manipulation, computation. That's what a blacksmith would do. You can imagine this being scaled up to being done with real machines. And again, you have way better control on this, and you can record everything that's done, so you absolutely know you have a good part. And by the way, forging gives you the very best properties you can possibly have. So this is a schematic of how this is done. This is another artist's conception of what this might look like. This is a forming system that has arms that hold, things that squeeze, sensors that work, and then you might have a thermal system. This is a close-up of what an interchangeable tool rack might look like. And again, this is our mission badge that shows the basic elements. If you look at this at a little more technical depth, what you really want to do is imagine you've got a part like this and break it down, and for each voxel within this, track the deformation as it goes through time, and what the temperature is. This is what a blacksmith is basically doing in his head. He knows what the critical temperatures are. He knows what will damage it or what will give it good properties, and you do that through those basic elements. What the report came out with was showed that this has a really strong value proposition, and these can be broken into 3 categories that you could read in the report if you like. It's economically and environmentally friendly. I'll say a little more about that. We can get great shape and property control because forging does a great job. And we can also do a great job with flexibility and accessibility. We can do things where they're needed, when they're needed, without big footprint or time required to get from point A to point B. So the actions that were recommended in the report, there's 7 of them. My favorite of these is to have a desktop prototype machine where you might have competitions, allow people to play with the software and get this out the way the MakerBot initially got 3D printing into the living rooms and kitchens of all kinds of geeky people. We'd like to see the same thing happen with this. The other thing that we kind of learned is it's natural. This will come, but it's also the 3rd wave of digital. Subtractive was the first. We really had to worry about machine and tool path. Where we've additive, we also had to worry about controlling the material state. We do metamorphic. We also have lots of forming strategies. What kind of tools do we use? We need more in the way of a sensor suite, control. And so this is naturally going to be the last of these 3 digital waves. We also found that this should be something that is very environmentally friendly. We built off of a report done by Gutowski at MIT, where he looked at energy usage and process rate for various techniques. And to make this a little simpler, processes concluded things like semiconductor oxidation, selective laser sintering and melting, fused deposition modeling. Here's big area additive manufacturing. And then here are more traditional processes, injection molding and injection molding and induction melting. And we can see that there are orders of magnitude differences where it takes actually a lot of energy to do a lot of these current additive processes because you make a powder, then you resolidify it. Melting doesn't take nearly as much, and you can kind of see that it takes more energy to vaporize. This is based on vapor. Melting, you've got a certain amount of energy you got to get in to melt things, and you actually need much less energy to deform things. So we think metamorphic can scale to big things and do it with relatively little energy. Big because we can have big presses, little energy because deformation really doesn't take that much energy to run. Other things we can do with this is we can use a wide range of established materials that are already used in forging. We're using established technology in open die forging, and unlike a lot of the things we do with selective laser sintering, where you get the best properties by hot isostatic pressing afterwards, that should not be required with this if you run it right. So again, we believe this is a process that should be better, cheaper, and more assured than any of the current digital manufacturing technologies. Again, if you compare this to additive, we can make lots of things this way. But again, metamorphic should have a wider range of materials, will consume less energy, should scale to larger sizes better, should give us better material properties, integrate with other processes, and we've got challenges. This is a fairly new technique is basically the problem. So at Ohio State, we are moving on. We're trying to develop this. We've already got a lab that has 3 robots in it. We're adding to it a forge and a press, and we'll be able to position things within this and do the same sorts of work you saw with plasticine, but do that with metal. And then the broader vision is to take shaping, basically adding things with weld wire and so forth, and cutting, put these all together, and we can make a whole bunch of interesting components by what we call hybrid digital manufacturing. And there's, again, groundswells of this, of some really nice work going on at Cranfield University, where they're basically adding and putting in some deformation to make some very interesting parts there also. This has all kinds of applications wherever high performance, low volume components are used, things like airframe, turbines, maritime, rail. There's lots of places this can go. And just to kind of end on kind of a fun note, just show that when you do things that are autonomous and controlled by robots, some very interesting things can happen. This is an example of Japanese sumo robot. And stop the volume on this, hopefully. Showing that these things can think, make decisions, and do things that a human can't do, and letting robots just go and doing things autonomous is the right way to do things, and there's lots of interesting things robots are doing now. You've probably seen Boston Dynamics with robo-dogs and robo-soldiers. There's robots making pizzas, laying bricks, all of that. This fits into the same vein. So let me end here. Again, these are the three waves. We've gone from subtraction to addition. Morphing, changing shape and properties, is the next logical thing. This should happen fast because the key things behind this are all moving quickly also. This can scale to large sizes. This should be a low energy way of producing things. We can get very good properties by leveraging all the metallurgical knowledge we have, and by recording everything, we have a natural path towards certification. So I will end there, and feel free to reach out through the internet and ask any questions that you might like. And thanks for